Okay, good day everyone. So today we'll be having a discussion about mechanics and hydrodynamic mechanics topic 12, which is the flow losses in pipes and fittings. So first we have to explain the flow losses in pipes and fittings and pressure loss caused by turbulent flow. So as you can see in the picture, there are pipes, for example, this pipe. So this pipe is a bending 90 degrees. So when first the fluid will flow smoothly in this direction, but as it reaches the bending, so there will be vortices in the flow, and then on this part of the pipe bend, so there will be a turbulence in that place. So in this situation, turbulence is starting in this flow. So on our 90 degrees bend or other bending pipes, also in pipes with sudden enlargement, so there will be eddies in here, in this part, or like a turbulence. And also if the pipe there is sudden contraction, so from bigger pipe, then it suddenly changes to smaller pipe, so there will be eddies in here or turbulence in these parts of the pipe. Okay, so as you can see, as the pipe changes, there will be turbulence. So as turbulence change, there will be pressure loss and there will be energy loss in the pipe or in the flow of the liquid. So the flow losses in pipes and fittings. So first we have the frictional losses. So friction between the fluid and the pipe walls results in energy losses due to shear stress. So turbulent flow increases frictional losses compared to laminar flow. Number 2, sudden expansion and contraction. So sudden changes in pipe diameter cause flow separation, leading to pressure losses. So energy is dissipated as the fluid adjusts to the new cross-sectional area. Next, number 3, bends and turns. So changes in flow direction at bends and turns create secondary flows and vortices, causing additional losses. So energy is lost due to the conversion of kinetic energy to heat or friction. Lastly, number 4, valves and fittings. So there will be flow losses in valves and fittings. So flow through valves, elbows, tees, and other fittings results in additional losses due to the turbulence and flow disruption. So these components introduce resistance to the flow, leading to pressure drops. So if you want to decrease, so losses will never be removed, but we can lower down the losses. So we will have to prevent this bends and turns, different sudden expansion and contraction to prevent further flow losses. Since valves and fittings or valves, we cannot really remove valves so that there will be no losses, because valves are very useful in a system. So we cannot really remove that, but we can just lessen the flow losses or the pressure drops during the flow of the liquid. Okay, pressure loss caused by turbulent flow. So increased frictional forces. So as turbulent flow generates chaotic eddies and vortices, increasing friction between the fluid and the pipe walls. So the higher friction force result in higher pressure loss along the pipe length. Energy dissipation. So turbulent flow dissipates energy through turbulent kinetic energy, converting it into heat. So this energy dissipation leads to pressure drops as the fluid loses kinetic energy. So pressure loss caused by turbulent flow is also number 3. So flow instability. So turbulent flow is characterized by flow instabilities and fluctuations in velocity and pressure. So these fluctuations cause pressure variations along the flow direction, contributing to pressure losses also. Next, the boundary layer effect. So turbulent flow creates thicker boundary layers along the pipe walls, increasing drag forces and pressure losses. So the interaction between the turbulent boundary layer and the core flow further elevates pressure losses. So these are why pressure loss causes, this is why turbulent flow causes pressure loss. Okay. Next. So cite onboard system examples of flow losses in pipes and fittings. So first, so there are almost all systems have losses, flow losses. So first, in main engine cooling system, so in pipes there are frictional losses occur as seawater flows through the pipes to the sea chest. So sea chest is also kind of a strainer. So in strainers, so there are flow losses since the sea chest is very big and the pipe is smaller than the sea chest. So it's like from a small pipe to bigger pipe, and then from bigger sea chest, then from bigger sea chest to lower pipe again. So there will be losses in that. So pressure losses can be experienced at bends, valves, and connections within the cooling system. Next, for fuel oil transfer systems, also the same, pressure drops may be present at fuel oil filters, valves, elbows. Okay. Next, for bilge water systems, pressure losses can occur at bends, strainers, and discharge valves in the bilge water system. So it is also encountered as bilge water is pumped out of the ship through piping systems. So for ballast water system, there are flow losses in pipes and fittings. So from pressure drops, we experience ballast tank connection, valves, and pipe junctions, and other bendings. So for firefighting system, there will be frictional loss may occur as water is pumped through fire main pumps to various hydrants and nozzles of the ship. Pressure loss can be encountered at fire hose connections, branch pipes, and fire hydrant valves. For freshwater supply system, there will be flow losses in pipes due to friction. And then for fittings, pressure drops may be present in freshwater pumps, valves, taps in crew cabins, and facilities. So there are almost every fluid on board ship has flow losses in pipes and fittings. So we cannot really prevent that, but we can decrease the losses if we want to. So just by improving the system. Okay, solve illustrative problems that determine losses of pipes and fittings in terms of its pressure. So as you can see in this formula, so to solve problems involving total head for a pump and system, we need to understand the concept of total head and how it relates to the pump and the system it is operating within. Total head is the total energy per unit weight of fluid imparted to the fluid by the pump, and it consists of several components including static head, velocity head, and pressure head. So the total head is equals to the sum of all the heads, like the static head, velocity head, and the pressure head, where static head is the elevation difference between the pump inlet and outlet. Velocity head accounts for the kinetic energy of the fluid as it flows through the system, and the pressure head, which represents the pressure energy added to the fluid by the pump. So let's solve an illustrative problem to determine the total head for a pump and system. Okay, so problem number 1. So a pump is installed to lift water from a reservoir located 10 meters below the pump inlet to a storage tank located 5 meters above the pump outlet. So the reservoir is 10 meters below the pump, and the storage tank is located 5 meters above the pump. So the flow rate of the pump is 0.05 cubic meter per second. Additionally, the system includes a section of horizontal pipe with a length of 50 meters and a diameter of 0.2 meters. So calculate the total head required for the pump and system. So to solve the problem, we will calculate each component of the total head and then sum them up. So HS is equals to HS is equals to H1 minus H2, which is 5 meters above, minus negative 10 meters, which is below the pump. So it is negative, so because it is below the pump. So 5 meters minus negative 10 meters is equals to 15 meters. So to solve for the velocity is equals to Q over A, which is equals to 0.05 cubic meter per second over the area of pi times 0.1 meter to the power of 2, which is equals to 1.59 meter per second. So that is V. So HV is equals to V to the power of 2 over 2 times gravity. Since V is equals to 1.15 meter per second, so we have to power it to the second power, put it to the second power, divided by 2 times gravity, which is 3.1416 meter per second squared, which is equals to 0.129 meter. So HV will be 0.129 meter. Well, for HP, since HP is 0 meter, since there is no information provided about pressure changes due to the pump. Now, summing up the components, HT is equals to HS plus HV plus HP, which is equals to 15 meters plus 0.29 meters plus 0 meters. So the total head will be the 15.129 meters. Okay. So that's it. Number 4. Explain the eddies formation due to sudden enlargement, track or contraction, rapid increase in pipe diameter, sharp bends, and valves. So as you can, this was already shown on our previous slides. So eddies formation in pipe system. So in here, if the pipe has a bend, so there will be eddies formation in the bending pipe. There also in the sudden enlargement of pipes, in the contraction of pipes, and different forms, other forms. So there are eddies formation in pipe systems. So first, for sudden enlargement or contraction, so if the flow here is smooth, as it enters to the bigger or enlarging pipe, so there will be eddies in this part of the pipe. While if it is a expansion of pipe, so this is for expansion, so there will be eddies if the flow will be expanded to another pipe. So how about in rapid increase in pipe diameter? So as the pipe diameter increases, also the flow is moving like this. So there will be eddies that will be formed in the pipe. For sharp bends, so there will be eddies formation in this part of the pipe and in this part of the pipe. For curved, 90 degrees curve, so there will be eddies in this part of the pipe. Okay, for valves, so as the valve is not fully opened, or there will be a okay, so there will be in this, if the flow is from here to there, so the flow here is very smooth, but at the back of this valve, so this is like a butterfly valve. So if you put the butterfly valve in this position, at the back of the butterfly valve, there will be eddies in this part of the valve. Also in this valve, so as the flow of liquid goes from top to bottom, so it's like an expansion of space. So in the expanding space, there will be eddies in the side of the pipe. Okay. So site onboard system, some example of eddy formation along pipes and other pipe systems. So in seawater cooling systems, there will be eddy formation. So first here in this one, in the sea chest, in the entrance of the sea chest, if there will be fouling, so there will be barnacles that is fouling the entrance. So there will be eddies formation in this part of the outside the ship. Okay, and then on the sea valve, so there will also be, so this is the sea chest, so the entrance of the sea chest, there will be a deformation in the valve. So there will be a deformation in the valve, especially if the valve is not fully opened. And then next is the sea strainer or the sea chest strainer. So some fouling, some garbage, or any impurities can create eddy formation. Also, if the pipe is small and then the CHS strainer is big, so there will also be eddies in that. So another valve, and then in the pump there will be eddies in the pump, and in the heat exchanger there will also be eddies. And then in the pipe, if there are bends, so there is also a overboard valve here, so there will be eddies all along the system. Okay, next, for bilge water system, there will be eddies from the filter. So we'll start from the bilge well to the bending of the pipe. So I couldn't really okay, and then to the filter there will be eddies. To the pump there will be eddies. To the bending of the pipe there will be eddies, and another suction here to the bilge water separator. So there will be different components inside that will create eddies. And for overboard, there is also an overboard valve, so that will also produce eddy formation on board this system. Okay, so for fuel transfer system, there are many valves. What else? Do you have filters in here? So if there are filters, there will be eddies in the filters. In the pipes, if there is a bending of pipes. Okay, in valves, so there will be eddies if the fluid is has very high velocity. So there will be high turbulence and eddy formation also in that part of the pipes. For ballast water system, so if you the ballast water system has filters, has UV reactor to kill the microorganisms. So it will pass through different pipes, valves, filters, pipe bendings, UV reactor, and different systems before entering the tank. So there will be eddy formation all over this system. So effects, so eddy currents may impede the smooth flow of ballast water, affecting ballasting operations. Okay. Next, for freshwater supply systems, so from tank to valves, through the pumps, through the hydrophore, through the bending pipes, so there will be eddies all over the system. So eddies can lead to uneven water distribution and pressure fluctuations in the onboard freshwater supply system. Okay, so that's it. So I hope you have learned something. So different pipings on board system has different flow losses and eddy formations and turbulent flows and etc. So I hope on board ships you can apply this information. So preventing or decreasing, we cannot prevent flow losses, but we can decrease the flow losses in our pipes. Okay, so I hope you have learned something today. Please subscribe and like and comment in our videos, and I hope you have learned something. You can use it on board ships, and good luck to everyone. See you on the next video. God bless.